Hello. Okay, so if you have any specific questions, we could go over that too, but we're going to do Math 75 review just to make sure you're up to speed with everything going into Math 76. So, am I just starting with the problems you gave me? All right.
So we'll just start with the basic explanation of derivatives.
Oh, and if you can you type your ID number into the chat so that we could just log whoever who's here? Thanks. Okay. Well, what are we doing? This is cool. Okay. So basics, you should be able to do derivatives. Right, when you see the derivative of x, you should already be able to do 1. Right, that should be easy enough. When you have something derivative of x squared plus 1, say, you know that you're only going to be taking the derivative of the x squared and not the 1. So that's going to be 2x as your derivative. Okay. Pretty simple. If you have harder ones, right, if you try and involve the product rule, so you have right, it's how do you take the derivative of this, right? You're going to do the product rule, so you're going to do derivative of the first one times the initial second one, so it's going to be 2x times the original, so it's 3x squared, or cubed, plus the derivative of the 3x cubed, so it's going to be 9x squared, times just the original, so it's going to be x squared. And then when you multiply that all out, you're going to get 6x to the 4th plus 9x to the 4th plus 36 x squared. And then from there, all you do is combine your like terms so that you would get something like 15x to the 4th plus 36.
How cool is that?
So this should be super basic. You should know how to do it by now, with the back of your hand, because they don't only get harder from here.
Yeah, see, these are back to Christmas.
And then same with the quotient rule. That should be pretty easy to do as well at this point. All right, so like if you had a problem, so if you had something like that, right, it's going to be the bottom times the derivative of the top.
All right, if you need any help, I'm just over here. There's a huge mess over here, so
Minus
you don't come over.
the top times the derivative of the bottom, all over the bottom square. Then from there, it's just making sure you do your algebra right. That's the hardest part there. Okay.
So go out of it.
So those, you'll be using those in the next couple of weeks, especially when you're dealing with the volume and area and curve, and especially when you start getting into integration by parts later on. So these will be very useful then. So to make sure you don't forget those rules. Let's see. Another thing that's very important at this point is when you're looking at a tangent line. Cool. So with a tangent line, right, we have to remember that is equal to the slope.
On the actual report. Yeah. On the actual
Is equal to the slope at a given point. And knowing this, we know that it has to do with the derivative. Okay. So if we're given a line and we're trying to find the tangent line, we have to take the derivative to even see what that tangent line is going to look like and how it's going to respond. So say you're given given an equation of a line of x, f of x equals 15 minus 2x squared, right? And it says find the tangent line at x equals 1. At x equals 1. So how would you do that? So first, obviously, you have to take the derivative, right? I'm talking to the camera, not you. But thank you for your affirmation, Tyler. Nope, so we're recording it. Okay, so first thing you have to do is take the derivative, right? Just like what we went over. So f prime of x is going to be negative 4x, right? And then from there, you plug in x of 1 to find, what are we trying to find, Tyler? When you plug in x of 1, we're finding the y value?
Yes.
Yes. All right. So we plug in that, so we're going to have f prime of 1, negative 4, minus 1, or positive 1, my bad. So the y value is going to be negative 2.
Those two, it's actually the rate of change. It's a slope.
Yeah.
It's a slope at the given
Sorry.
point.
So this is going to be the slope, so that when you go back, you can figure out how the line is going to look at that given point. Man, this is going really fast. Okay. So once you figure out your slope, then you can look at the point on the graph. Pretty basic, hopefully.
Yeah, look at how happy I am.
Do you want another example?
No, do you want to do a few?
It's okay. I'm gonna keep running.
Okay. Okay. So, real fast, we'll go over limits. Right, so when you're doing a limit, it's how you're approaching a point on a graph. You will be using this again later in Math 76, but it's always good to remember now so that you don't forget it later. So limit, right, if you have, for example, limit
Yeah, I'm gonna have to.
x approaches 1. Okay, I'm going to do my homework 2x squared x minus 1. So how are you going to solve that? So basically you're going to plug in 1 and see what happens. And if it works, then you're good. If it doesn't work, like say you get 0 on the bottom, then you have to do L'Hopital's rule. Take the derivative of the top and take the derivative of the bottom independently. So if you plug in 1, right, it's going to give you 0 on the denominator, which we don't like. So we're going to take the derivative of top and bottom. So we're going to get negative 4x over 1. And again, we're going to do the limit as x approaches 1. Right, and from here, if we plug in 1, it'll be easy. So we get negative 4. And we don't have any complications with the denominator. So that's the simple one. Again, when you have larger ones, like say, limit is x approaches 5. Number t minus 5. So again, you have to take the derivative because if you plug in 5 directly, it's going to give you 0 in the denominator. So once you take the derivative, you get 3t squared minus 12 t over 1. And then from there, we realize that if we plug in 5, it'll be okay. So we plug in 5, so we get 25 times 3, which is 75. And then 75 minus 60, so it's going to be 12. Or sorry, 15. Can't do math this way. Okay. So those, keep in your back pocket because they'll come up pretty quickly throughout the semester. Something that you will definitely see at this point in the semester are your trig identities. Hopefully you know those. If not, we'll go over them right now.
So based on what there's on research.
So
Now, one thing I would always say is don't grab
if you have sine, you have to take the derivative. It's going to be cosine. So I'll just write them all out. Sine of theta
you can test and they're asking you
is going to lead to.
and if you get then the question is going to be nearly impossible. Because you got to be able to identify which one's the top, which one's the bottom, how they look, what the area should roughly
Anyway, so sine theta is going to be cosine theta. Make sure you know that. Right, but if you do cosine, it's going to give you a negative sign. If you do tangent, it's going to equal secant squared,
No, you can erase all that.
and so on and so forth. Let's write them all out. E over d theta secant is going to be secant theta, tangent theta. Just from experience, these are probably going to be your most common ones. You should know the ones for cotangent and cosecant as well, but they're not as likely to be used in your problems just because they're a little bit more difficult to deal with when you're taking integrals. Okay? Also, so going off of the triggered enemies, make sure you guys know your unit circles because you're going to use that a lot, especially when you start dealing with the radians of your areas and volumes under the curve. So if you memorize the unit circle, that's great. I actually don't have that memorized and wouldn't really be able to help you with that very well. But essentially what it is, circle, you know that your x-axis has to do with cosine, right? Because cosine of 0 is 1, cosine of pi is going to be -1. Sine is going to deal with your y-axis. You're going to have sine of pi over 2 is 1, sine of 3 pi over 2 is -1. Those are like your go-to, make sure you know those by heart. Let's see. The way I remember the circle is I actually draw the triangles.
Do you want me to write it down?
What?
I could write out the circle if you want.
I mean, if you want to.
Okay.
Yeah. Tyler can actually show you how to write out the entire unit circle.
So the great thing about the unit circle is if you have, here's your unit circle. The great thing about it is that each quadrant is just an extrapolation of the previous quadrant. So as long as we remember this first quadrant here, we can copy and add that to itself for the remaining of them. So in each quadrant, you're going to have 3 lines, one for 30 degrees, one for 45 degrees, and one for 60 degrees. At 0 degrees, we know that it's going to be 0 to pi. Right? This is going to be pi over 6, pi over 4, pi over 3, and pi. Now, if we want to get the remaining of these, it's just going to be that copied over. So we know that at here, our sine of our sine of pi over 6 is going to be 1/2, and our cosine is going to be root 3 over 2. At pi over 4, both are going to be root 2 over 2, and at pi over 3, it's going to be opposite. So it'll be sine is 3 over 2, and cosine will be 1/2. And this adds on itself. So here, we know that's going to be pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. And it copies all the way around. The only thing that you have to remember is that in the first quadrant, sine and cosine are both positive, so that tangent is positive. In the second, sine is positive, cosine is negative, so tangent is negative. And then both sine and cosine are negative in the third quadrant, So tangent is positive, and then sine is negative here, cosine is positive, tangent is negative. If you're able to remember that, and at the very least remember that first quadrant, the rest of the inner circle is just that added on itself.
Cool. Hopefully that makes sense. If you're like me, and you don't feel like actually remembering how to draw the unit circle and thinking about it all the time, I just draw the triangles. So then it's, so your 45, 45, 90 triangle, it's going to be set up as 1, 1, square root of 2, right? Just based on the Pythagorean theorem. And so that, oh, if I have sine of 45, okay, so it's opposite over hypotenuse, so it's 1 over root 2. And then like if you have like the 30, 60, 90 triangle, then it's going to be 1, root 3, and 2. So then if I have a sine of 30, 1 over 2. If I have a cosine of 30, then it's going to be 3 over 2. So either way works. Just make sure you remember these by heart before your first test. Okay. So what else do we have? So we're going to go into implicit differentiation because it'll actually come up a little bit later.
All of this. So you can subtract
Okay.
all of this.
So those of you who are kind of shady on how to do implicit differentiation, it's the same thing as a derivative. The only difference is that you're just acknowledging what you're taking the derivative of next to it. So like if you're taking the derivative of x, if you take a derivative of y, you're going to write y prime or dy to acknowledge that you did that step as well. Okay. If you guys just joined us, if you could type your ID number into the chat just so we can have a log of who showed up, that'd be great. All right. And also, if you guys have any specific questions, feel free to ask us, and we can answer those questions too. So if we have an example of implicit differentiation, so take the derivative of x squared plus y squared equals 25. Right, so if we do implicit differentiation, right, we have it in respect to x. So when we do the x, we're going to get 2x. It's going to be dx over dx, right? So we don't actually have to worry about that one. But with y, when we take the derivative, it's going to be 2y dy over dx, right? And we're saying basically we took the derivative of y when on the problem is saying with respect to x, just to simplify it. Okay? And then 25, that's going to be 0. Right? Another way I'm going to write this is going to be y prime, just so it's a little less messy. And then this, we said, is going to disappear. So you get 2x plus 2y y prime equals 0. And then from here, what you're going to do is solve for y prime to figure out the slope of the graph. What?
Think about words.
Right. So when you do this, you're going to get y prime equals negative 2x divided by 2y. Right? So basically negative x over 1. So then when you're looking at, say, a tangent line, this will help you out of what's going on and how it's looking. So, like say, if it asked, find the slope of the line at the point, say, 3, negative 4, all you do, since you have basically the slope, right, you're just going to plug it in. So it's going to be negative 3 over negative 4. So your slope for that at that point is going to be 3/4. Right? So this stuff, you want to make sure that you don't overthink it because it's going to come back a lot. Okay. Another one you guys probably all remember are related rates. So it's a little bit more difficult. Just because of word problems. But it's the same premise of what we're doing with all the derivatives. So say we have the problem, and it's a little bit long, so I'm just going to read the problem and I'll write down the numbers on the board. So, example, air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. What is the rate at which the radius of the balloon will have a diameter of 20 centimeters? Alright, so what's important here? We know the rate at which it's growing, and we know when we want to look at it, right? So if we write this out, so we have the velocity, right, or the volume change in time is going to be 5 centimeters cubed per minute, right? Important piece of information that you're going to use later on. And what you're trying to find is RT, right, is going to have to do with the size of the balloon. Because you want it to be, why did you write 0/2?
It's D, it's diameter.
Oh, sorry. Right, so we know that R of T, when we're looking at it, is going to have to do with the diameter divided by 2, right? Because if we're looking at the radius, so that's going to be 10 centimeters. So hopefully you guys remember the volume of a sphere. If you don't, make sure you brush up on that because you'll start using volumes and areas of different objects, especially with the area under the curve and volumes under the curve. The volume of a sphere is going to be 4/3 pi r cubed, right? And we said that our radius is going to be 10 centimeters. So if we plug it in, 4/3 pi.
Yeah, we kind of put Susie in.
No, actually, my mistake. We don't actually plug it in yet, right? Because we're looking for the rate at which the radius of the balloon.
This one would be.
Yeah, we're looking at the rate, right? We're not looking at time. So because of that, we have the volume formula. We know what the derivative is equal to. So what we need to do is first take the derivative of the volume formula. So when you take the derivative of this, it's going to be 4 pi r squared, right? Because the 3 is going to cancel out with that 3 when you're doing the derivative. And then again, when we include the implicit differentiation, we're going to include the r prime. So from here, what we're going to do is plug in the r squared, and then we know b prime of t is equal to 5. So we plug in, and we're going to solve for r prime. So 5 equals 4 pi times 10 squared r prime, right? And then once you solve for r prime, you're going to get r prime equal 1/80 pi, and that's going to be centimeters per minute. Okay. So just to recap, we're looking for related rates. We have the initial rate that the balloon is being pumped into, right? The acceleration. And we're looking for the rate at which it's going to be growing when we reach the diameter of 20 centimeters. So we had to use, find the radius, which is just diameter divided by 2. And then we had to know the volume formula. So those are the 2 critical points. And then from there, it's just taking your derivative and plugging it in and making sure you don't make an algebra mistake. Okay. As a side note, especially with all of the volume under the curve and area under the curve problems you guys will be having, make sure you watch your algebra, because I'm sure most of you guys will be able to just do set up the problem, which is actually the hardest part, and then you'll just mess up the algebra and oh, what happened? So always check your math.
So I think we just move the button.
So,
So with, I think it is called.
higher order derivatives. So, it's the same thing as taking a regular derivative, except you're going to do more. Oh my gosh. Do you want to do any of these problems?
I'll do those.
All right. Okay. So higher order derivatives, same sort of thing, except you're going to do it multiple times. And this is actually going to help you later down in the road. Closer towards the end of the year, but it's still good to remember it now because then it'll be really easy later on. So if we had f of x, 5x cubed minus 3x squared. So if we had this problem, it says I want to find the third derivative of it, right? So we're going to take the derivative. First time, it's going to be 15x squared minus 6x plus 10. So that's our first derivative. Then we go from here, do our second one. That's double prime x. It's going to be 30x minus 6. And then our third derivative is going to be 30. That's how you would do that. On a graph, essentially what's happening if you were to graph these is that the line is going to become simpler and simpler until eventually you end up with y equals 30, and it'll be a flat line. If it doesn't get simpler while you're doing the derivative, go back and check your work.
With calculators, when they're trying to read in degrees, minutes, seconds.
Also, important to remember, right? Your first derivative is going to help you figure out the slope of the tangent line, right? We went over that. And then the second derivative is actually going to help you figure out the concavity of the graph. So is it going up, right? Or is it going down?
Another special character, another special character.
Okay.
You have to do one special character and then another.
Okay, so going off of the concavity and everything, we'll go back to a related rates problem and determine the critical points using our derivatives, and then figure out whether we have concavity or not. No, we'll just do the critical points. We'll keep this one simple. So say you're given f of x equals plus 33x to the fourth minus 30x cubed plus 100. And it says, I want the critical points of this graph. So, all you do, right, we're going to take the derivative, we're going to get 30x to the fourth plus 132
Put radians and merge degrees minutes
x to the
seconds.
third minus
Why is it
90x.
5.64
Right. From there,
seconds?
we're going to set f prime x equals 0. And we're going to solve. So what can we actually factor out of this? We can factor out we can definitely factor out an x squared. I think the highest number we can factor out of this is a 6. So 6x squared, we'll pull that out. And what are we left with? We're going to be left with 5x squared plus 22? Yeah. 22x minus minus 15. Right, from here, so we can automatically take the 6x squared and just set it equals 0. So one of our values is going to, for critical points, is going to be 0. So one of our values x equals 0 from the 6x squared. And then we're going to break this down. So we have to factor it down. And hopefully you guys remember, you can either use the quadratic formula, or you can use the diamond method, or yeah, just those two, or any way that you figure out the combination of how to factor this. But when you actually do break it down, it's going to be 5x minus 3 times x plus 5.
Sort by big.
So after you do the algebra, that's what you get. Then you're going to set each part equals 0. So 5x minus 3 equals 0. And x plus 5 equals 0. Right? So your other critical points that you're dealing with are going to be x equals negative 5 and x equals 3 over 5.
This one? Oh, I typed in
So,
1.217.
These will be your 3 critical points.
I can't.
So if you were asked, say, if you're asked for an interval of where the graph is increasing or decreasing, then you would look at points around these 3 and see, is it going up, is it going down, and what's happening. Because it's kind of hard to actually graph x to the 5th, x to the 4th, x to the 3rd, something like that. So you're just looking at certain points after you take the derivative, which will be easier on you. So, do you want to go over the maximum and minimum, Tyler?
Sure, you want to write up this stuff for me?
Sure. Okay, so we're going to switch it over to Tyler. He's going to start maximum and minimum.
All right, so you need help? Just ask, are you doing homework or?
Okay, guys, so on a graph, there are absolute minima or maxima and local minima or maxima. So we know an absolute maxima is going to be the highest, or for maxima, it's going to be the highest point on the entire graph, whereas a local might be on a specific range that we're given. So if we're looking at, say, this graph, and it does something like this, it's going to go down, back up, it's going to go up and over here. Something like this, like that curve. So we know we are going to have an absolute minimum here, since this is lower than any other given point on the entire graph. And we're going to have an absolute minimum here. So that's higher than any other point on the graph. But we also have local minima or maxima on the graph, whereas right here we have a local maxima, here we have a local maxima, and here we have a local minima. Now all of these can be determined based upon the graph and critical points we find from the slope and concavity, which we'll get into later. So we're going to do a quick example just to kind of explain what it's going through. Is that if we're looking at the graph, f of x is equal to x squared. We're going to do it super simple. We're going to say f of x is x squared, and we want it on the range -1, 2. Okay? So we're going to set up our graph, and we know that at x equals 0, we're going to be at 0. At x equals -1, -1 squared is going to be 1, and then 2 squared is going to be 4. So 1, 2, 3, 4. It's going to be something like this, because we're restricted by the range of the graph that we are given. So we have a couple maximum and minima here. So we know that we're going to have a maximum, an absolute maximum of x of 4 at the x value x equals 2. That's because that is higher than any other point on this graph. We're also going to have an absolute minimum of 0 at x equals 0 right here. And we're going to have a local maximum of 1 at x equals -1. So a lot of these problems are going to be application problems. So they might have a question like this on a larger graph, much more complicated, and asking you to explain the change of something as it goes along on this graph and how that might affect the data points that they're giving you. So if we are, this can also be applied to the change of rates and shape of graphs. So we're going to kind of go into that next. So shape of graphs is going to be based upon the derivatives and second order derivatives. So we know that we went over a little bit about higher order derivatives, where if we're given a function, we can take the derivative not once, but twice, or even more than that. So if we're given a graph, we're given the graph f of x is equal to negative x to the fifth plus 5 over 2x to the fourth plus 40 over 3x to the third plus 5. Right? So we're going to take the derivative of that just to find the slope at any given point. So f prime of x is going to be negative 5x to the fourth plus 10x cubed plus 40x squared. And if any of you are just jumping in, I would recommend if you're confused by this step, that you go back in the video or go on to a couple of sites we have. Come into the tutoring center, we can help you out with just basic derivatives and how that works. So we got a derivative, and we're gonna factor that down. So we pull out a 5x squared. So that leaves us with x squared plus or minus 2x minus 8. Okay. And then we can factor that down a little bit more to try to find our critical points. So negative 5x squared times x minus 4 x plus 2. Okay, so now we're going to have 3 critical points. At x equals 0, negative 2, and 4. Okay? So with those, we can actually write down a number line. So here's our number line. We're at x equals 0, x equals negative 2, and x equals 4. So the biggest thing that you got to do is you have to plug in points in those specific areas, explaining why or the directionality of the graph. So if we plug in something, for say, into our f prime, we plug in negative 3. We want to plug in points in between these 3 different things. So we plug in f prime, negative 3 into f prime, we get negative 315. Okay? That's just by plugging that straight into this equation. So if we have negative 315, we know that f prime of 0, or f prime of x is less than 0. So that'll give us a little example as to how the shape or the directionality of the graph is going. So if we plug in negative 1, we're going to get f prime of negative 1 is equal to 25. So we're greater than 0, right? So we can, I think the way I used to do it is I put minus signs or plus signs in the ranges depending on the directionality of what we're achieving. If we plug in 1, f of 1, we get 45, so that's positive. And then if we plug in f of 5, which is out here, we get negative 875. So we're going to be negative. Okay. So now, based on this graph, we know a couple things. We know that from negative infinity to negative 2, we have a decreasing slope. From negative 2 to 4, we're increasing. And from 4 to infinity, we're decreasing. So something just along the lines, this is just general shape. It'll be something like this. We don't know what exactly, but we can tell kind of the overall shape of it. The next step would be to take the second derivative of this. And if we took the second derivative of this, we could determine the concavity of each piece within here. So it would be the exact same method. You take the second derivative, you'd find your critical points of your second derivative, which are now not critical points, but are points of inflection. Points of inflection are where you shift from a concave down to a concave up, or vice versa. So concavity, this is, I'm going to write up here. So if I'm arching like this, my concave is down. Whereas if I'm arching like this, I'm concave up, like a smile. So that would give us concavity, and that would allow us to further draw out this graph. And based upon that and this, we could determine where we might have absolute minima, absolute maxima. Like at this point, we know we probably have a local min, right? Because it's decreasing, and we don't really know what's out here. It's going up for the rest, the slope wise. So unless we're given a specific end of our range, it's either coming from infinity or a definite point, which could be potentially an absolute maxima on this graph, considering we have a local maximum over here somewhere, a local maximum at 4, a local min at -2, and a potential local min or absolute min at whatever the end of our range is over here. So if we were going to determine the concavity of this, we could take the derivative. I'm going to erase this right here just so we could talk about that next. So if we're going to find the concavity of this point, we're going to find f double prime. And your teachers will probably go over this a little bit more in class just to make sure that you guys recall the topic, and they'll go through the application of this process. So f double prime, we're going to get -20 x cubed plus 30 x squared plus 80x. Okay, so right off the bat, we can pull out a 10x at the very least. So we pull out 10x, we're left with negative x squared, or negative 2x squared plus 3x plus 8. Now, if we were going to finagle this around, I don't believe, I can't think of anything off the top of my head in order to get this down. But the good news is most of them will factor down to a lower degree of your leading coefficient. It'll be much easier. But in order to do this, what you need is, at the very least, we have a point of inflection, POI, at x equals 0, and your other 2 points of inflection would be based upon this equation, the negative 2x squared plus 3x plus 8 that we found from determining the second derivative. We would do that with Pythagorean theorem and be able to solve for the final 2 critical points of the or points of inflection of the graph, and that would give us the overall shape. And a lot of times they'll actually have you describe the shape and then draw it out, or say, okay, so from here to here, where are we going? Are we going down or up? Vice versa. Okay, so the next topic that we're going to talk about is the first derivative test. Actually, I think I almost went into this just a little bit, but if we're looking at a graph, we can determine relative mins and maxes or absolute mins or maxes based upon the first derivative of that graph. If any of you are just joining, make sure that you guys sign in with your ID number into the chat, just so we could see kind of who's been here and who's coming through these things. We're trying to do more videos and post them so that if anybody's unable to come to any tutoring, that they could come and watch these videos and get at least some help. Okay, so back to first derivative test. First derivative test gives us relative values of our graph. So if our f prime, if our first derivative, our slope, if our f prime of x is greater than 0, then our x value is going to be a relative max. Okay, at the end of that slope. If our f prime of x is less than 0, then then our final x value after that section is going to be a relative min.
I hadn't read
And if
Have you looked it up online?
this is going up to a critical point, so like if I'm going up to a critical point and I have f prime of x is greater than 0 up to that point, that's going to be a relative max. But the only difference is if both sides, if f prime of x is positive on both sides,
Because I've never had to deal with that.
or negative on both sides of a critical point, it is neither a relative min or max. Depending, it would be a relative max or relative min, but it's not. And the reasoning behind that is if we're looking at the number line, right, and we have our critical points here, 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 and I'm going positive in between that, from there to that critical point, positive from this critical point to this critical point, and then I go down, and then down some more, right? The overall slope of that graph is going to be going up consistently to here, and then down to here. So we're going to have an absolute min down here, but we're not going to have an absolute max at this critical point. The reasoning behind that is that once we achieve that critical point, we might have a point of 0 or undefined slope, but after that, we're still going up. So there's no relative mountaintop, essentially, to look into. So it would be at this point, because we see the shift from positive to negative slope. The same goes for the other direction. So we're not going to have a relative min here because there's no indentation or valley to be looking for. So we're going to do a quick little example of this topic just to do an overview or explanation of it. So if we have the equation g of t is equal to t times the cube root of t squared minus 4. Now, that's another thing that is really important for you to realize is that the cube root, or actually let me write that bigger just so you guys can see it better, that the cube root or any square root is, you can rewrite it as an exponent, okay? So if we have that, we're going to find our first derivative, so our g prime of t. So we know this is going to be product rule. So the derivative of t is 1, so we got t squared minus 4, and I'm going to rewrite it with a fractional exponent. So t squared minus 4 to the 1/3 power plus 2 over 3 t squared times t squared minus 4 to the negative 2/3, right? Because we're at the 1/3 power, and we're going to subtract 1, so now we're at negative 2/3. Okay, so simplify this just a little bit, rewrite it just so it's a little easier to gauge. So we got t squared minus 4 to the 1/3 plus 2t squared over 3 times t squared minus 4 2/3 power. Okay, because if you have a negative exponent, as you can say, you just shift the side of the fraction. So if I have a negative exponent on top, it's going to go into the bottom of the fraction. If I have a negative exponent on the bottom, it's going to go into the top of the fraction. So from here, we're going to multiply this one by the denominator in order to get like fractions and combine them. So when we combine them, we're going to get 3 times t squared minus 4 plus 2t squared. That's all over the denominator. 3 times t squared minus 4 2/3. Okay? And then we're going to rewrite that now. We're going to combine like terms. So 5t squared minus 12 over 3 times t squared minus 4 2/3. Okay? And now I'm going to turn the camera just a little bit just so I could kind of, no, actually that doesn't work. We're gonna rewrite that over here. We're gonna rewrite that up top. I'm gonna erase all this, and you can skip back in the video later if you need to look at how I got to that point. So 5, we found that d5 of t is equal to 5t squared minus 12 over 3 times t squared minus 4 is 2/3. Okay. So now we need to find our critical points. So we know that any critical point is where the slope is equal to 0 or it's undefined. So we know that if the only way that we can find an undefined answer is if the bottom, the denominator of the fraction, is equal to 0. So if we set this denominator equal to 0, we can see that t squared minus 4 is a key portion of that section. T squared minus 4 cannot equal 0, right? So if we know that t squared minus 4 it can't equal 0, we know that we're going to have at least, at the very minimum, have 2 critical points at t equals positive or negative 2. Okay? And then the other step of that would be looking at the top. Since we know that only thing that will make the denominator 0 is if t is positive or negative 2, now we want to look for where if the equation gives us a 0 function, we set the top equal to 0. So we set 5t squared minus 12 equal to 0, right? All we have to do is add over our 12, divided by 5, and take the square root. And we're going to get a positive or negative square root of 12 over 5 as our other 2 critical points. So now from this, we're going to actually draw our number line. Okay, so here's 0. Here's the square root of 12 over 12 over 5. Here's 2, and vice versa. Okay. So we're going to try it. Essentially what we're going to do is just like normal, we're going to actually input values within these critical points in order to determine if the system is increasing or decreasing along this number line. So if we plug in a negative 3 or a number over here, we're going to get a positive answer. So we know that it's positive out here. Okay. We're going to plug in negative 1.7 or something along that line, and you're going to get a positive answer. Right? Yes. Yes. So we're going to get a positive answer, and it's going to be increasing here as well. So 0 is not a critical point. I was just putting that in for reference. But we can plug in 0 into the equation. If we plug in 0 to the equation, we are also going to get, we're going to get a negative answer. So it's going to be decreasing from negative root 12 over 5 to positive root 12 over 5. And then if we plug in 1 in here, it's increasing, right? So we can now explain the overall shape or directionality of the graph. So we can say that it is increasing on the range of negative infinity is less than t is less than negative 2. It's also increasing from negative 2 less than t is less than the square root of 12 over 5. And then it's also increasing from the square root 12 over 5, which is less than t, less than 2, and then from 2 less than t is less than infinity. Now the reason that we are actually splitting these